Assalamualaikum warahmatullahi wabarakatuh, and very good day to Dr. Kamarul and friend. My name is Muhammad Daniel bin Muhammad Dia, and my partner in this project is James Banda and Maxwell Chambakata. The title that we chosen for this project is the temperature sensor for wind turbine monitoring system. Now we go to the background. Wind turbine is a device that converts kinetic energy from the wind into electrical power. A wind turbine monitoring system is responsible for monitoring the tower blades, shaft, gearbox, generator and overall condition in generator compartment. This involves a variety of sensors such as accelerometer, encoder, temperature sensor, liquid level, particle counter, voltage, current and humidity of the sensor. So, the scope of this project only cover for the temperature sensor installed in the generator compartment used to monitor environmental condition in compartment so as to protect part from being damaged by inappropriate temperature. So, for the design stage, first, it is the transducer selection. Second, what we do is calibrate at 0 degrees Celsius with the resistance 100 ohm. After that, we define the signal conditioning. After that, we go for the analog to digital conversion, which is the ADC selection. And lastly, we do the error analysis in this project. Okay, now we go for the sensor selection. The sensor selected for this project is analog temperature transmitter of the T91 model series to match the specific requirement of our project specification requirement. The temperature transmitter convert the temperature dependent change in the resistance of the resistant thermometers. The temperature dependent voltage change in thermocouples into 0 to 10 volts or 4 to 20 milliamp output signal. The standardized signal measuring temperature value can be transmitted simply and safely. From the figure below, we can see that the temperature sensor for T91. This picture taken from Wika datasheet TE91. We select the model T91 which is PT100. Now this is the specification of the PT100. So the important parameters in this sensor is the maximum span, the analog input with 0 to 10 millivolts. After that, the response time is less than 0.1 second. And lastly, the maximum current supply of the sensor, which is 40 milliamp. Okay, now we go to the transducer selection, which is transducer design parameter. So in our project, the resistor temperature detector of PT100, we consider it as it has two wire with thin film 1/3 class B with tolerance at 0 degrees Celsius equal to plus minus 0.1 degrees Celsius and 800 degrees Celsius plus minus 0.27 degrees Celsius. So the transducer details, the advantages it is a simple configuration. For the drawbacks, this accurate lead wire resistance and its variant to temperature cause measurement error. And way of minimizing it, we choose to make the wire short. For sensor calibration PT100, the transfer function is R equal to R0 times by 1 plus temperature coefficient by the change of the temperature. For the selector sensor, we consider that the temperature coefficient is equal to 0.00385 ohm per degree Celsius. So at temperature 0 degree Celsius, the R equal to 100 ohm. So to convert the resistance change into the voltage output, a null Wheatstone bridge will be used in this project. Now we go to the sensor calibration of the Wheatstone bridge. We can see the R3 is the 2-wire RTD transducer. The Wheatstone bridge, which is a temperature transducer with the input of 10 volt. So we can see that to the signal conditioning, it is between the temperature difference of V2 minus V1. That's all from me. Thank you.
Hello, my name is Maxwell, and I'll present from sensor calibration and Wheatstone bridge. So the following errors have been neglected in our calculations: dispersion power error, lead wire resistance error. The dispersion power error will be neglected because the sensor that we chose, according to the manufacturer's manual, we were not provided with the dispersion power constant. And the lead wire resistance errors, because we have used a two-wire RTD, so we'll make sure that the lead wires will be as short as possible so that we minimize the errors due to wire resistance. This sensor will be calibrated, or the system will be calibrated at a temperature of 0 degrees Celsius. So essentially, an RTD this RTD at 0 degrees Celsius will lead a resistance value of 100 ohms. So in converting this resistance value into a voltage value, we have used a Wheatstone bridge. So in using the Wheatstone bridge, we set the values of R1. So basically, this is the Wheatstone bridge. So we set the value of R1 and R2, fixed values 100 ohms. So now we know the value of the RTD, we know the value of our three fixed resistors. Now we can find the value of the resistance in the potentiometer, which is the variable resistor in this case. And doing the mathematics, the value of the variable resistor of the potentiometer was found to be 100 ohms. So basically, this figure here illustrates the literature that have been explained. The resolution. Our system we have designed it in such a way that we want the ADC to record up to a resolution of 1 degree Celsius, a change of 1 degree Celsius. So from the RTD transfer function, the resistance value of a change of 1 degree Celsius was found to be 100.385 ohms. So during the calculations, finding the potential difference, it was found to be 9.6 millivolts. That is, for a change of 1 degree Celsius, we're going to have a voltage signal of 9.6 millivolts. So therefore, the resolution of our system to detect a change of 1 degree Celsius is 9.6 millivolts. Signal conditioning part 2. So there is a need for signal conditioning in this for a phase 2. One for signal attenuation, amplification. 2 to increase the signal strength. So essentially the signal strength will be increased by including or incorporating voltage followers which have high impedance. And number 2, signal attenuation. This is going to be done with an aid of a differential amplifier. And the design requirement is that we need to amplify the maximum signal to 10 volts. This is supposed to be 10 volts. We need to amplify the maximum signal from the Wheatstone bridge to 10 volts. So the maximum temperature reading that we expect from this system is 100 degrees Celsius. So a resistance value equivalent to 100 degrees Celsius based on the RTD transfer function is 138 ohms. So working out on the Wheatstone bridge, converting that value into a voltage value, we have a voltage potential difference of 798 millivolts. So we are going to use the differential amplifier in amplifying this voltage signal. So we have chosen a differential amplifier with a gain of 12.5 and a reference voltage of 10 watts. And an inverting op amplifier with a unit gain and 10 volt reference voltage. So we need to convert 0.798 volts into 10 volts. We need to amplify that to 10 volts. So the gain is found to be 12.5. So that being the case, the values for these are the respective values of the resistance for our differential amplifier. So we're going to have our RF there as 105 ohms, and the other as 10 ohms, 10 ohms. The other one has 105 ohms as seen from the figure. So this configuration will give us a gain of 12.5, which will boost our maximum signal of 0.98798 millivolts to 10 volts. So in a nutshell, this is our signal conditioning circuit. So basically the signal conditioning circuit, the first part is the Wheatstone bridge, and then the second part is where we have the differential amplifier. So basically the Wheatstone bridge signal conditioning is there to change the resistance values from the RTD into voltage values. From this, my friend James will take you through. Thank you very much for your attention.
Hi everyone, I'm James. I'm continuing where Max left off. So in this next slide, you can see it's a continuation of the signal conditioning, whereby we have a circuit and there's a differential amplifier, and then additionally to the differential amplifier we have added an inverting amplifier, so that our signal, if it is changing signs, this is controlled by the non-inverting amplifier there. On the next slide is a complete drawing of the instrumentation system that we have designed, from the sensor to the differential amplifiers and the OP amplifiers, and all the way to the ADC. So the next slide, I'm going to talk about the design of the ADC and how we made the selection. So in terms of the selection of the ADC, we looked at the change in temperature that we would like to detect, and therefore we calculated the resistance equivalent value, from where we were also able to calculate the corresponding change in the voltage, which we used as our system resolution in terms of changes. So for the system to detect a 1 degree change in temperature, the voltage has to vary by 9.6 millivolts. And then from there we were able to use the equations for wavelength, whereby the change that is detectable is equivalent to the total voltage of the system divided by 2 to the power n, where n is the wavelength. In this case, the unknown value was the value of n. We know that our system is operating at 10 volts as reference, and the delta V there is 9.6 millivolts. So therefore we divided the voltage divided by 9.6 millivolts, which gave us log 1000, and then we took logs so that we could come up with the value of n, which was 9.96, which we approximated to 10 bit. So this is the wavelength of our system, in other words the resolution of the ADC that we are going to use for our system design. So the system is going to operate on 10-bit ADC and a 10-volt reference voltage for our application. There are many ADCs that are out there with this kind of parameters. So we chose the one that is the model CHT ADC10, which is manufactured by Sisoid. This is the ADC that we chose, and you can see now the ADC we're talking about is this one, and this is where we're going to position our ADC. At this point, reached the end of our presentation. Thank you so much for your time. Thanks.